All right, great. So today, thank you for all being here. Obviously, my name is Ben. I work with WellTyped. I've worked on GHC for a while now, and I guess today we're going to talk about the runtime system. But really, more than that, we're going to sort of pick up on what Sebastian left off at, essentially starting with a review of our evaluation model, since it's pretty tricky to understand what the runtime is supposed to do unless you know sort of the environment that it's supposed to be providing for the program that's being run. So first, I'd like to sort of get a quick show of hands here. Who has actually looked at the heap of a Haskell program before, or has a rough idea of like what this? Oh, that's actually a good number. Okay, that's reassuring. And I guess does the word capability, does that mean anything to people? Oh, okay, this is good. This is good. Okay, so I think we can probably leave it there then. And we can. No, we will actually, we'll do a quick review. So, right, we're going to start sort of today by looking at the general responsibilities of the runtime and, sort of what is the runtime actually supposed to be doing with respect to its interactions with the mutator, which is the program that the runtime system is running, right? This is, we're going to review quickly the heap structure, which is a rather important component of the runtime state of the program. We're going to look at how the runtime is actually providing that heap structure via a system known as the storage manager. We're going to look at some of the concurrency primitives that the runtime system uses to implement GHC's green threading model. We then are going to focus rather briefly on some elements used for GHCI and interactive execution, and then finally some sort of hard-earned tips and tricks on how to debug both runtime, the mutator, as well as the runtime system itself. And hopefully, we're going to get some questions from you. So please, if I'm going too quickly, let me know. I'm happy to stop and sort of we can slow things down a little bit. Or even if you think, oh, there's no way you know what your neighbors are, but if you feel that we probably are going too slowly, that's also, I'm happy to, certainly if there are any concrete questions, let me know. So let's start by looking at GHC as a whole, right? So this is GHC in sort of a nutshell. And here we see that, well, nowhere on this picture, short of this little box right here, does the runtime system appear, right? This is the compiler pipeline. And the insight here is that really GHC comes in two halves, right? We have the compiler, which is responsible for emitting object code of some form, either bytecode or native code, perhaps WASM or something of the sort. And then we're going to also have a corresponding system, the runtime system, right? And that is this here, the sort of slice in between here, if you will. I'll try to use my mouse, actually, for the benefit of those online. We have this slice in between here, sitting in between the operating system and, again, the mutator, which is, just to remind you, the program that we're running, which might be object code or it might be bytecode. All these components in between are the runtime system. And the runtime system provides a multitude of services to these layers above and provides sort of an abstraction layer on top of the operating system, among other things, right? So when you allocate an array, that's going to be handled by a primop, a primitive operation provided by the runtime system, or writes to an mvar, create a thread. These are all things that are handled by C++ code provided by the runtime system. We have the event log and the tracing infrastructure used by the mutator, potentially. We have a linker, which is capable of loading and unloading code at runtime, and a scheduler for, again, green threads. And then we have all of this bit off to the right. This green bits are the storage manager, which consists of sort of a hierarchical allocator, a two-level hierarchy of allocators, and a set of garbage collectors implemented in terms of those garbage collectors, allocators rather. And so ultimately, we're going to cover a good number of these topics in some amount of detail. We're not going to cover all of them deeply. We're going to cover, get sort of a taste of what each of these things do, how they do it in many cases, and why. and that's really the goal of this talk. Is you should know roughly the pieces on this slide and where to find the relevant machinery in the code. So, but again, to start off, we're going to quickly recap the execution model that we expect the runtime system to provide. And so, sort of recalling that from yesterday, we have this notion of the STG machine. This is the abstract machine that GHC implements for Haskell evaluation. And we're going to note here that this bit here is essentially the STG machine as originally proposed by Simon, I think almost 30 years ago now. It was mid 90s, I believe, this paper was originally published. And we've sort of taken some liberties with it in GHC. So we've made we have these registers here, these general purpose registers. These are a set of registers, a family, essentially one family per runtime representation supported by the compiler, right? So for instance, we have these general purpose R1 through, it's actually R10 typically, but which are capable of holding, just either bytes like an int hash or an int16 hash, or also pointers, right? Pointers to lifted objects, for instance, boxed objects. We have these registers here, which are floating point single precision registers, some double precision registers, some SIMD registers. These things are all used for passing of arguments to and from functions, or arguments and results to and from functions, as well as sort of as intermediate for intermediate values in some cases. In addition, and these are the things that are going to be used by the mutator. In addition to those general purpose registers, we have a set of special registers that are sort of used at times by the mutator, at times by the runtime system for sort of bookkeeping. So for instance, to take one example, we have this current TSO register, which is going to record the identity of the current Haskell thread that is executing on this STG machine. We also have the CCCS register, which is used for the cost center profiler, tracking the current cost center stack of the execution. So we have this sort of family of registers, and the reason why we have these is because on modern hardware, it's very beneficial to be able to make use of machine registers. And one of the most reliable ways to make use of machine registers is to make these manifest in the intermediate representation, the abstract, the machine that you're compiling to, which in this case is this sort of C++ or STG machine. And we can, in some cases, map these C++ registers, these R registers, for instance, can be mapped to machine registers, right? The hardware, the native registers of the machine. So when you're writing to R1 on x86, 64, for instance, you're actually writing to, I believe it's RBX, the machine register. And that makes for a very nice code generation story with predictable and relatively good performance. Of course, in addition to these, oh yes, of course, we have some questions.
Yeah, well, I was a bit surprised to learn that there's a fixed number of registers, a limited number of registers available here. Because usually when I've seen virtual machines, they have sort of unlimited registers, because the idea is when you map it onto real hardware, then you do the register spilling.
That's right.
But it seems like here, wouldn't we have to already do some register spilling on the virtual machine? And then what if your real machine has more registers? Then
that's
wasted.
Yeah. No, both are good questions. So these are what we call the global registers of the C++ state. There's also the ability to, in a C++ program, you can define sort of variables. And we actually call these things local registers, because they're sort of local within a scope, within a procedure. And these things are going to be then either assigned, placed in a general purpose register, or in a machine register if possible, or spilled. But the global registers are always going to be, sort of assigned to a machine register. And then we have a register allocator that will handle placement of the local registers. And this is sort of the abstract machine, right? And that we're looking at here. But in general, we're going to perform register allocation, in sort of a later step in the native code generation pipeline. We're going to do register allocation to assign the local registers to machine registers when possible.
But do we do spilling on these
Sorry.
general purpose registers?
So these global registers, if a global register is live, then it will live in a machine register. Now, they are typically only live across function calls. So that is to say that typically when you're doing a function call, you will find the value of R1 in RBX. But if you are within a function, then the R1 may not be live; it may be dead. There may be no sort of value user of it later on in the function. In that case, you might be able to reuse RBX for some other, for a local register, for instance.
But what do we do if we run out of general purpose global registers?
At a function call.
Yeah.
Yeah. Well, that's right. That's exactly right. So yeah, let's see. So we are going to. In this case, we're going to spill to the stack, right? So you'll note that one of those components on that last slide was a stack, right? And that's going to be used for the passing of excess arguments and the spilling of, the passing of excess results, right? So if we have more arguments than we have global registers to pass those arguments in, then we're going to place those excess registers on the stack, right? On the Haskell stack. And that's a fairly common pattern, right? This is the same as you'd find in C, right? Under a C calling convention, for instance, you'd pass the first few registers, first few arguments typically in registers, in machine registers, and then anything that doesn't fit, you'll place on the stack.
So I think at the level of STG code, you won't see any of this register stuff. It's just a little functional program. And we translate to C++ with procedures, C++ with parameterized procedures. You still won't really see much of these global registers, not the ones for parameter parsing, right? So if a function's got 17 parameters, just give it 17 parameters. But then there's a stage which every compiler has to have, at which you've got to say, okay, what is the calling convention for an x86 or for PowerPC or for something, right? And then you need to know how many registers you got. Now, one way to do that is to delegate it to LLVM and say, LLVM has control of the stack and spilling and all that, right? But in GHC, the stacks live in the heap. They're garbage collected objects. The garbage collector traverses them. So we took the choice a long time ago, for better or worse, that GHC has control of the exact layout of those stacks, right? We do not delegate that to some, back-end code generator thing. So there's a C++ stage. It's called the sort of continuation parsing thing, which we say, take C++ with procedures and move it to C++ without procedures, but with we explicitly establish a calling convention at which we say, okay, parameter 1 goes in register 1, parameter 2 goes in register 2, and floating point parameters go in floating point registers, and at that stage we need to know how many real registers there are, okay? And excess ones will go on the Haskell managed stack, and we generate explicit code to put them on the stack, okay? And it's because we want control of the stack, and we don't want to delegate that. Does that make sense? So, yeah. But this is at a pretty late stage. STG, nothing. C++ with procedures, nothing. Then do the CPS transform on C++. All this becomes manifest.
Okay. And at that point, you know what the native architecture is.
At that point, you have to know how many registers of what kinds there are. Then, and we still call them R1 and R2 and F1 and F2. Then the final stage, which you generate, bits. Then you need to know that R1 is called, I don't know, %EAX or some nonsense like that. Okay.
It's RAX. Yeah, that's right. Oh no, it's quite. That was great, Simon. Thank you. But in addition, we use the stack for a few other things. And again, these will look somewhat familiar from yesterday. We have the stack is used for managing or for tracking continuations of case expressions, as we'll see in a slide or two. We use it for tracking update of thunks under evaluation and exception handlers. But really saying that we have a stack is really not sort of strong enough yet. We need to sort of define how we're going to represent that stack on the concrete machine that we have. And in the case of GHC, and Haskell programs more generally, because of laziness, it tends to be that you can sometimes get very large stacks. So the usual approach that a language implementation might use in an imperative setting, where you have a monolithic stack of fixed size or bounded size, that then you have to, and you will just crash if you exceed that size. Well, that's not a great solution for a GHC in many cases. It is, yeah. So what we rather do is we use a chunked stack representation, where we're going to augment this machine model here with two additional registers, SP and SP lim, which are going to point into a heap object, as Simon said, which is representing the stack, or rather a chunk of the stack. And these chunks can be linked together via these so-called underflow frames, which are normal, relatively normal stack frames, which when entered will essentially, if we pop an underflow frame, we will then advance the stack to the previous chunk, right? And so in this way, we can sort of incrementally grow the stack and incrementally shrink it as needed. So this is obviously quite nice. If you're a Haskell user, you don't really need to worry about your stack usage. And if you have something like a Thunk leak where you might build up a very large stack, your program's not going to suddenly die unless you run out of memory, right? As I said, now this is sort of to look at the first concrete example of how all of these pieces fit together here. We're going to consider this program here to see how the stack and the registers that we've seen sort of interact in a function call and case analysis setting. So here we have this program, foo, as a binary function with 2 arguments, a and b. We have a case, which is going to scrutinize f of a, and then is going to return to this continuation here, right? This is where the result, the evaluated result of f of a, we're going to sort of think of this as core, right? So this case is actually driving evaluation. We're going to then pass the evaluated result x to this other function g. Now, the thing to note here is that g, that's continuation rather, we're also going to pass b, right? So the continuation is free in this second argument. And so we need to somehow ensure that that second argument, that b, remains sort of available to us in the continuation after we have called f, right? After we have scrutinized this scrutiny here. And so if we look at the C++ that this program is going to produce, we're going to find a few things, right? So we first note that we pass the arguments a and b in global registers, right? This is what I said. These registers are used for argument passing. So a is in R1, b is in R2, etc. We're then going to say push a return frame, which is going to identify the continuation we're going to return to after the scrutiny has finished evaluation. And we're going to, again, push all of the free variables of that continuation into that stack frame. All right, and so we're now here just manipulating these, the stack pointer register to do this. And then we're going to set up a call to enter the scrutiny. The first argument of f is we're going to pass a. So there we go. We set up the calling convention, and then we'll eventually call f. After f eventually finishes, well, it's going to jump to the top of the stack, which in this case we're going to find is xret, right? This xret here is what we call a return frame, hence the ret, and the x here is named after the case binder of this case analysis, which is x in this case, right? And so xret is going to simply unpack the continuation frame that we previously pushed, right? So we know that we can find b on the stack, and x is going to be the results from our call to f, the scrutiny, and we're going to find that in R1. And then we can set up a call to g, right? So this is sort of how the operational model that you should have in mind as you're thinking about case analysis and function calls. And right, so this is what the stack will look like after we've pushed our return frame up here. We have the stack pointer pointing to our return frame with 1 free variable in it. And then after we pop it, we're just going to end up back in a stack that looks something like this. So that's the stack. Are there any questions so far? Yes.
Can the CPU predict what is going to happen after the function is called? Because normally you have a call and then you have a ret, and here it seems like you just have a jump and then another jump. How does that work with the CPU's prediction?
Not terribly well. In many cases, unfortunately. This is one of the costs of our of our execution model. Actually, is that because we don't actually use the C stack, and our stack doesn't. Our stack register is actually a different register than that used by the C stack in most of the architectures that we support. We don't benefit from the optimizations that the CPU performs, with respect to stack returns and such, which is a bit of a shame. And we've not really characterized how much of an effect that has on modern hardware. yeah, it would be an interesting thing to check. On the other hand, we use the design that we use for a good reason, and that is foreign calls become almost trivial, right? Because we don't use the same data structures, for our stack as the C does. And so if you want to perform an unsafe foreign call, you need to do very little to set up that call. You don't need to switch stacks, which is a nice property, but it does come at a cost. And it not only at runtime potentially, again, we have not characterized recently, but also in the just observability, essentially, right? The tools that you can use to analyze a C program generally aren't going to work terribly well on Haskell. So this is something we've actually tried to address in the past for observability reasons. Try changing our stack model to be more like a C program. It does come with some costs, though, and it's not a clear win. We've not looked at performance, though.
On that same topic about being able to reuse some of the optimizations that CPUs have for C code. So if you were ideally you would want to use call and return, but isn't it true that we can't really easily use call and return because where we want to return to is not actually where we called from. We want to return to slightly later for various reasons.
You could use return, I think, but you would not necessarily be able to use call. That's right.
Yeah,
because call does assume you're returning to the
pair up
next
the call and
instruction. Yeah,
return.
that's right. Yeah.
And it's the pairing up the call and return.
Yeah, that
the
will
CPU
allow those
relies on.
optimizations to fire. I think that's probably true.
Would you be able to explain briefly why that is?
Why
we can't use call and return?
Yes. Okay. Yes. Sure. So many architectures. I don't want to get too deep into this because we are time is critical here. But yes, many architectures will provide explicit instructions for calling functions, which will assume that the essentially, in addition to jumping to a particular function, will push to the stack a frame that will encode the return address directly after that call instruction. And then a paired return instruction, which will essentially return to the frame at the top of the stack. And so this is what a C compiler would typically use in its call, in a function call setting. As Duncan said, not really possible in our case because we do not use the stack register that a C compiler would in again most cases, and secondly because we are often not returning to the successive instruction, the next instruction after a call. We're going to return to some elsewhere, to another block entirely. And so that, given that these two instructions, call and return, are often what drive these microarchitectural optimizations that allow sort of efficient predictable function calls and returns, we don't get to benefit from those. Yes.
This is a question from Gergo Erdi.
Yep.
It says, does that SP equals SP minus 2 assignment compile to something complicated that checks to make sure we don't need a new frame chunk? Or by this point, do we know we won't, so we can just safely slide a pointer?
I forgot to mention this, actually. Yes, we are here omitting for simplicity a so-called stack check. We will see this in a few slides. I meant to mention that. I apologize. Thank you, Ergo. That's very well noted.
And then one more question
yes.
from Eduardo. Is it significant, the performance that we lose due to this absence of CPU optimizations?
Yeah, again, I can't speak to that at the moment. I have not characterized on modern hardware. It's likely measurable, but beyond that, I won't speculate.
Just trying to follow what this stack data structure is. You're indexing it with numbers. Are those like items on the stack or byte offsets?
Words.
Are they of uniform size? So you could have an item that is multiple words.
That's right, yes. So this offset is in words. I should have mentioned this as well. So yes, in Haskell in general, both in the heap context and in the stack context, sort of the basic unit of allocation and sort of object size is the word, right? We will not have something smaller than a word, and we measure offsets typically in terms of words. And so this is actually a bit of a lie, actually. That 2 should be, okay, so I wrote this C++, and hence you will see that it will look very much like this should be 16 and this should be 16. There's a macro in the runtime system that we use to compute sizes in terms of words, and that's what we think in terms of. But yes, that should be 16. That is true. That's ultimately SP is an address. Again, encodes an address, and that's all right. So any further questions or? All right. So in that case, we will move on. We will briefly discuss the heap. The relevant thing as far as the heap is concerned, and the mutator's interaction with it, is allocation, right? That's referring to existing heap objects is just a matter of dereferencing a pointer. That is not something that requires sort of intervention from the runtime system. However, allocation is, right? We need to allow the this program running on this machine to be able to allocate new heap objects. And for this purpose, we provide it with a nursery, which is a block of free memory identified by 2 additional CMM registers, HP, the heap pointer, and HP limit, the limit pointer, which sort of delimit this block of memory, which we call the nursery. And what this is going to be used in a sort of bump pointer manner. So if the mutator needs to allocate 8 bytes, then it will simply place its 8-byte object at the current value of HP and bump HP by 8. And it will continue to do this for every allocation until it hits the end of its block, at which point it will garbage collect potentially. We'll see the details of how that heap check and how that garbage collection process works a bit more concretely in a few slides. But this is sort of the rough idea. So what does a heap object look like? These things that we're allocating are themselves representing many things, right? Not just Haskell constructs. So this is one of the themes that we find in GHC's runtime system, is that the heap is used as much for bookkeeping as of internal state as it is for Haskell state. So we represent nearly a good fraction of the sort of internal state of the runtime system as heap objects. So threads and stacks and the messages used to pass events between various core operating system threads and STM transactions, all of these things are themselves heap objects. And heap objects, this actually allows us a number of nice properties. So for one, we don't need to sort of come up with bespoke systems for managing lifetimes of all of these objects and garbage collecting them and the such. We get them for free from the garbage collector. And moreover, we can reuse object liveness, reachability, for other purposes. So for instance, deadlock detection in GHC is simply an application of, well, we can see a thread is deadlocked by checking whether it is still reachable from the heap, from any of our roots. So if it's reachable from a run queue, then obviously it's not deadlocked. If it's reachable from a thunk that it might be blocked on, then, well, that thunk is, if that thunk is reachable, then there's a chance it will be unblocked at some point, etc. We have, so threads we rely pretty crucially on reachability for things like deadlock detection. We sort of get that for free, avoiding from the garbage collector, avoiding a lot of bespoke logic. So putting a finer point on it, a closure is going to look something like this, right? This is the STG closure type. This is the generic closure type, all closures. And when I say closure here, I mean heap object. We use that word fairly loosely in GHC. A closure is always going to consist of a header followed by 0 or more payload words. And those words here are identified as being closures themselves or pointers to closures themselves, but in general they may not be. They may also just be a 64 bits or a word hash or something like this. So the type here is a bit of a lie. That header is going to consist of an info table pointer followed by maybe a profiling header if we're compiling profiling, etc. We won't go into profiling in this talk. It's a bit out of scope and fairly easy to read up on your own. I'd encourage you to do so. But that's yeah, so it's a very straightforward sort of layout, right? Just one word header in most cases and some number of payload words. The meaning of those words are going to depend upon what kind of object we have, of course. And the kind of object that we have is determined by that info table that closure header pointed to on the previous slide. And that info table is going to encode quite a bit of information, some of it for the benefit of the mutator, some of it for the benefit of the garbage collector. Things like the closure type, is this thing a constructor or a weak pointer or a thunk, an indirection, an STM transaction, etc. It will contain some description of the layout of the payload, so how many words we expect in that payload and which of those words are pointers that need to be traced by the garbage collector. If it's a function, it will contain the arity. In general, it will contain some entry code, which will be, in the case of a Thunk, for instance, like the code that will actually evaluate the Thunk, the right-hand side of the Thunk, or in a function, the code of that function. For funcs and functions, in some cases, it may contain a reference to a so-called static reference table. This is for the garbage collector, for static objects. We won't touch this. We're not going to discuss this in this talk. I'm happy to go into it after time, but this is a bit of it brings us a bit too far afield, so we're going to put that aside for now. You can see the definition of SCG info table in infotables.h. I'd encourage you to look at it. Very straightforward type, but it will look something like this, right? And in particular, with a few tweaks, because there are a few optimizations that we use here. For one, one of the things that I had made reference to in the previous slide was that we have in the info table some reference to entry code, right? And one of the most common things that a program in Haskell is going to do is enter a closure, all right? So one way, the naive way that you might think we can keep track of entry code is to, well, in the info table, just have a pointer to the code, right? Another pointer, another field in that info table, which will refer to the entry code. And this would work, of course, but it is costly because that means every time a mutator thread needs to enter, for instance, this closure here, I apologize, we would need to first look at the info table pointer and then dereference that and compute the offset to the code pointer and then look at the code pointer, and then we can finally jump to that code, right? And that's actually a significant cost in many cases. You take an additional cache miss in the worst case, and that's quite something to avoid if you can, given how common this operation is. So in GHC, we will often, on many platforms, use an optimization known as tables next to code, where we will instead use the info table pointer of a closure to not refer to the info table itself, but rather to refer to its entry code, instead placing the info table directly prior to that entry code. So its location is computable via an offset of known size, but that means in the very common case that we want to enter, for instance, a Thunk, we can simply jump to this pointer here, right? The closure info, the info table, the closure's info table pointer, and that will bring us directly to the entry code of that Thunk. Heap objects in general, so we'll now look at a few examples very quickly, just to give people a flavor here. Are there any further questions? Yes?
Does the memory, virtual memory, allow us to execute that code directly? Isn't that supposed to be a data space?
So this is actually an interesting point, and it is slightly problematic in some cases. Yes, there are so memory protections. In this case, you do have to treat this as both sort of code and data, and increasingly, platforms are making it very difficult to treat memory as both code and data. So reading from code is verboten in many cases. That is something that may become an increasing problem in the future as these sort of security measures become more common. Yes, but that in general, up until now, it's been a surmountable problem. No platform that we target on a first-class manner has been rigid enough in that protection requirements to be problematic. OpenBSD, I think, is the exception, maybe. This is a read-only structure here, and this is obviously code, so that's also read-only, right? Read, execute. So it doesn't require writable code, which is good. But yes, increasingly, as I said, even reading from code sections is becoming problematic. Again, we're going to take a very quick detour here, looking at a few concrete examples, and then one more example on looking at Thunk, how Thunk entry and allocation works, and then we're going to turn our focus to the runtime proper. So here we have a small program, Haskell program, allocates 4 things on the dynamic heap. We have this constructor here. It's an application of the iHash constructor, which is, of course, the data constructor of the int type. And it has its structure is exactly as one would expect. We have an info table pointer pointing to an info table, which says that the thing is a constructor, and it has one non-pointer field, right? That's the n pointers here stands for non-pointer, and that field is precisely the 42. It's the payload of the int, right? That's the int hash field of this constructor. Now, something to note here, of course, is that if we had another ihash application, we would reuse this same info table, right? This is a static data structure. It's emitted in the code of that the compiler would emit, and it will be used for any ihash application. Okay. We also have thunks, of course. So this thunk binding here is going to be, have a similar info table. This time it's going to say that it's a thunk, and it's going to have one pointer field, and that's going to precisely be the free variable, the single free variable con of this thunk. And in addition, we have one extra field here. This is known as the SMP header. This is where once that thunk has been evaluated, final result of that thunk evaluation is going to be placed. This is what we call the SMP header, or the indirect T, as we'll see. We'll see how this works in a couple of slides. Again, we have, moving to a slightly more complex case, we have a binary data constructor in this case, but there's really no difference structurally, right? We have two fields instead of one, both pointers. And then we have finally this last case here, which is a selector thunk, the first function of the pair type. And that is, of course, going to select out the first field of this pair. And because the garbage collector, the reason I bring this up is that in general, when there is additional information needed for a sort of class of objects, we will place that information in the info table. Right? So in this case, we need to know, because this thing is a selector thunk, and the garbage collector does implements an optimization known as the selector optimization, we need some way to encode which field that selector should be selecting. Right? This is one of the requirements of the selector optimization, and that information is encoded in the info table of that closure type of the first function. And otherwise, though, it's a thunk. Right? So we distinguish it as a selector thunk, but otherwise normal thunk. Yeah.
Full of con, that's a thunk, and first of pair, that's a selector thunk. But to me, both of those look like just function calls. So do you know in core a difference between a selector and a function and STG?
Yeah, that actually is a very good point, because this is actually a lie, isn't it? Yes, I apologize. Yes, this should be an application of this thunk should be an application of the first function, not the first function itself. That's right. The same with thunk. And I might have given it the proper name here. Yes, I did give it the right name. Okay, so yes, we will see how applications work in the next slide. So I'm going to put that aside for now, if that's okay. But the point that I wanted to bring up here was that the info table pointer can contain information that is sort of specific to a closure type. And that is that was the thrust of this particular example. So let's see how applications work now, actually. So in particular, we're going to focus on partial applications. So if we consider an undersaturated function application, so for instance, this function app is going to take a function, a binary function, and a single argument, and apply that single argument. If we look at what the CMM of that function app is going to look like, it will be something like the following, where we have, we're first going to sort of unpack the arguments, and we're going to set up a call to this SCG app p fast function. Now, this function here is one of a family of so-called fast application functions, which are generated by GHC's build system when you compile the compiler by a utility that you can find in utils/genapply. This utility will generate a bunch of these functions, which will, in general, for a variety of call patterns, one function per call pattern, inspect the closure type of the applied function and determine whether the number of arguments that we are applying to that function saturates it. All right? If so, it will set up a call and jump to the function's entry code with the appropriate arguments. If not, it will allocate a PAP closure. which PAP here stands for partial application. Now, as I said, there's a family of these functions. So in this case, we're looking at a single pointer application. That's what this P means. You might have, if you have 2 pointer arguments, however, you'd see an app PP fast function instead there. If we look at a concrete case here, like this foo here, which we've applied to X, we're going to end up with a heap that will look something like this, right? Where we have a PAP object, which is going to record not just the remaining arity of the function, right? So that's the 2 arguments would be needed to saturate foo, because we've applied 1 argument to it, X, and the function is, of course, foo. And that's going to, so this is going to give rise to this sort of heap structure. Of course, now we've touched upon a good number of heap closure types, but there are many more. We're not going to go over all of these. This is sort of a summary. Maybe you can peruse them at your own on your own time. But the point is here that in addition to having
Sorry,
closures
can you
representing.
return to the
Oh yes.
previous slide?
Sorry.
Can you return to the previous slide?
Of course.
So here I see that the PAP closure has 0 pointers, although the heap
Yes.
object has 2.
That's right. So that is, so I breezed over that in the interest of time. But yes, the point here is that the layout of this particular closure, and there are other closure types that share this as well, is not determined by the layout fields of the info table. This is actually determined by the closure itself, right? So the number of pointers you have here in this argument list is going to be determined by the nargs field here in the closure, not the info table, right? Because it depends upon how many arguments you have applied. That's sort of a dynamic thing. Does that answer the question, or? Okay, great. Further questions?
Yeah, so I was on the next slide. I
Yes.
was wondering, perhaps ahead of time, but is there a particular reason to have a special type for selectors and not treat them just as
It is
regular types?
specifically for these sort of cases. This optimization, the selector optimization, essentially the selector optimization is a GC optimization that allows the garbage collector to do some sort of partial evaluation or evaluation of these sort of selector thunks, so if they are applied to a constructor, right? So if you have first of a pair, then the garbage collector can actually evaluate that. And that actually is an optimization that can allow you to eliminate certain classes of space leaks. There is a paper that I can refer you to on this, but that's the whole reason why the selector case is handled explicitly here. So we have as well, various arrays and mutable variable types. We have, and various bookkeeping closures that we will see the role of in the coming slides. One final example here before we carry on towards the runtime system itself. To see how all of these pieces fit together, we're going to look at a very simple program. We are going to allocate a thunk. We are going to pack it into a solo constructor to ensure that it remains a thunk. And then we're going to enter that thunk. And we're going to walk our way through the execution of this program and sort of characterize how this interacts, how this is lowered to the STG machine. We're going to begin sort of where Sebastian left off. We can look at the simplified core with the ddump simple flag, as Sebastian had noted, to ensure that the program is sort of, GHC is doing what we would expect, in core at least, right? And here we see that's generally the case. However, since core doesn't really precisely track allocation, we see that thunk has been inlined. But if we proceed to STG, which as we will in a moment, we will see that that allocation will again be explicitly represented. Of course, we've not really seen STG yet, so I'll take a moment or so to introduce some syntax here. STG, very similar to core in its syntax, but with a few embellishments, right? So we have, again, the closures here are introduced by a lambda. That doesn't necessarily mean the thing is a function. That just means it's a closure. And the type of closure is determined by this update flag here. So for instance, in the case, followed by a set of arguments, right, and the right-hand side. So here we have foo is a function, which is a reentrant closure with one argument, x. And the right-hand side, in the case of a thunk, we will find that the update flag is maybe updatable if it's an updatable thunk, or if it's a single entry or non-updatable thunk, it will be S, as we see down here. But in all cases, we may also find that the thing has some a set of free variables, which we represent explicitly in the syntax. And then, in the case of a thunk, we'll have obviously no lambda binders. So that will hopefully be sufficient for our purposes here, allow you to sort of inspect the STG of our program here, right? So, and I realized here that the free variable list is missing. I apologize for that. There should be that should be free in n. But yes, so we have here foo in STG. We again have a let allocation of the thunk itself. And we see here that the right-hand side of foo, the final result, is going to be an application of the solo constructor. However, this thunk is, we see, an updatable thunk. Obviously, no lambda binders, and we see it has the right-hand side we would expect. Okay, great. Now we can look at the C minus of this program, and we can sort of get a sense of what it's going to do on the machine. So we're going to first, by looking at how much does this program, this function, need to allocate in order to, potentially. And we see that it needs to allocate 5 words, 2 for the solo constructor and 3 for the thunk. That's 40 bytes, of course. So we increment HP by 40. We're going to check to make sure that we're still within the bounds of our nursery, and then we will dispatch accordingly. There's a question.
There are 2 questions, both from Adam Essie. The first is, when is a single entry thunk not updatable?
Oh, well, always. That's so single entry. These are essentially synonymous. So if I think Sebastian also made mention of this optimization. Thunks, you might think, well, we need to update them to ensure sharing. However, if we are guaranteed to only enter that thunk once, we only use that value once, well, then there's nothing to be shared. And so there's no benefit to performing that update, and we can elide it.
And then the second question, also from Adam, is what does updatable mean?
We will see that in just a moment. Essentially, this is how we achieve sharing. And let's, I'll leave it at that for now, and we'll see in 2 slides, I believe. Okay, so we have, right, if the heap check is okay, then we're simply going to populate the allocation that we just reserved up here. And that will give rise to a heap structure that looks something like this, where we have, here's the solo constructor, our thunk, with, of course, encoding a free variable. And we're going to then save this result into R1, as this is the result of our evaluation, and return to the top of the stack. Now note here that there is this offset here. While the solo constructor starts at HP minus 8, we say that our result is actually HP minus 7. And this is due to another optimization that GHC performs known as pointer tagging, where, if you recall, I said at the outset that the sort of minimum size, allocation size of a heap object or a stack frame, anything in GHC's sort of memory model, is a word. And consequently, we can ensure that any pointer to any sort of Haskell heap object is going to be word aligned to 8 bytes, for instance, on a 64-bit machine. This means that the bottom 3 bits are going to be always 0, and we can reuse of a pointer, that is. And therefore, if we have a pointer, we can use those bottom 3 bits for our own purposes. For instance, to record the identity of the data constructor to which that pointer refers. If it's a data constructor application, for instance, or if it's a function, maybe the arity of the function. But in this case, we are referring to a solo constructor, and that is the first constructor of the one constructor solo type. And consequently, we tag this with a 1 tag. The code generator can then use that to more efficiently lower case analysis. Okay, so we now have thunk so we've examined the case of thunk allocation. Now let's look at thunk entry. What happens when we actually enter the thunk that we allocated previously, right? So we're now looking at this binding here, this S11E binding, which is an updatable thunk, as we saw. And this is going to be relatively similar. We're going to first perform a stack check. And the reason for this is that after we need to somehow record the fact that after we have finished evaluating the right-hand side of this thunk, we want to make sure that the thunk is updated to become an indirection pointing to the result that we evaluated, that it evaluated to. All right, and again, this is because of the we want sharing of that result. If we have another user of that thunk, we don't want it to recompute it. We want it to use the result that we already have. And so we do this by way of the stack. We're going to push a so-called update frame to the stack, which is a 2-word frame. Hence, we're going to check to make sure that we can push 2 words without overflowing our stack. And consequently, if the stack check finishes, we're going to push that frame and enter the right-hand side of the thunk. We'll see in just a moment what happens if that if either a heap check or stack check fail. That's coming a bit later. Finally, we have the update process. All right, so we saw previously that we will enter the thunk and its right-hand side, but we have not actually done anything to mark the thunk as being under evaluation. And that's not ideal because, well, if another thread finds that it needs to enter this thunk, we may want to suspend that thread. And rather than redo all the work that's currently being performed by the original evaluator, we want to instead just suspend it and wait until that work is finished, and then we can reuse that same result that the first thread had already evaluated. So we do this in one of 2 ways, depending upon the so-called blackholing strategy in use. This is a compiler flag, essentially. If we are strictly blackholing, then we will essentially, at the moment we enter the thunk, overwrite the thunk with a black hole, as we see here. So we're going to update the header of the thunk to, instead of pointing to the info table of the thunk, instead refer to this black hole info table, which is going to record the fact that somebody has this thunk under evaluation. And the SMP header that we saw previously, the indirect T, is going to point to the thread object that is evaluating that thunk. Then at some point, that thread will finish the evaluation. That will allocate some, in this case, an iHash constructor. And at some point, it'll reach the STG update frame that we previously had pushed. And that will be responsible for updating the indirect T of this black hole to point to the final result. This is now an indirection, right? We now say that this thunk has been updated to become an indirection to its final result. This black hole, so in this way, this black hole closure type is sort of used in 2 ways, right? It's used for recording indirections as well as sort of in progress evaluation. As I said, there are sort of 2 distinct ways in which we might handle blackholing, eager and lazy. In eager blackholing, we black hole the thunk as soon as we enter it. In the lazy case, we will actually wait until the thread that is evaluating needs to suspend. This is a slight optimization because it means we have slightly less memory pressure, bandwidth pressure. Yes?
This is a question from Eduardo. He says, why do we need this black hole intermediary thing? Can't we just point to the shared evaluating TSO, if I understood things correctly?
Shared evaluating TSO. So the TSO is a thread. So that's TSO here stands for thread state object. I suspect I had not mentioned that up until now. So that is actually the thread that is performing the evaluation. And indeed, while the thunk is under evaluation, the black hole will point to the TSO object that is evaluating it. And I would just like to point out that this is the same. What we have done here when we've black holed this thunk is actually overwritten the thunk. Right? We've not allocated a new object. We have simply overwritten the info table to turn that thunk into a black hole. So this is a mutation of the existing object, not the allocation of a new object. And then eventually, once we finish evaluation, we will, in fact, turn this into an indirection by making this black hole instead refer to the final result and not a TSO. So sort of you can read black hole as being essentially we often think of black holes as being the intermediate value, a placeholder saying that a thunk is under evaluation, And then after it's been evaluated, we refer to the thing as an indirection. And which state a particular black hole closure is in, whether it's a black hole, a proper black hole marking a in progress evaluation, or an indirection to a final result, depends upon whether this indirect T field refers to a TSO or to a Haskell value, like a closure or of a constructor. Yes?
Couldn't you overwrite the info table back to a thunk once you finished evaluation, so you wouldn't have this weird thing where the black hole means two things?
You wouldn't want to evaluate, you wouldn't want to rewrite it back to a thunk, because that would mean you would lose sharing, because you'd then not know that somebody has evaluated it. Now, I suppose you could rely on the indirect T field and see, is the indirect T field a valid object after evaluation? So you ignore the info table.
But don't you still have to do something like that here, because you have to look at the field of the black hole and see, is it a TSO? If so, I have to wait, otherwise carry on.
That is right. Yeah, you do.
So if you overwrote the info table to something that said fully evaluated indirection, then clients could then just take the next field and not.
Yeah, so if you had indeed, we do have an indirection info table as well. And that is not used for sort of evaluated thunks. There's a reason for that. It's an optimization, actually. It ends up being an optimization. It makes some concurrency situations a bit easier to work with. I think this brings us a bit far afield, though. So let's. I'm happy to talk about that after, though. It's an interesting question.
Sorry, also just one other quick question.
Of course.
Maybe you'll talk about this later. Presumably, something clever happens if the thread that's evaluating a black hole has there's an exception.
Yes. Yeah. That is that is definitely an interesting case. And yes, we will unwind the stack and essentially suspend the state of any black holes under evaluation. And I'm going to suspend now, actually. So I think we actually, if that's the final question, we can pick up that during the break if you want. But that break begins now, I believe. If there are any further questions, after this, we're going to pick up again with the runtime system proper. And hopefully,
Welcome back from the break, everybody. I realized that I forgot to introduce Ben at the start of his talk. No offense was intended. In some ways, Ben needs no introduction, right? He's been a leading developer of GHC for a decade now. He does amazing things. He works full time as a compiler engineer at WellTyped. In the past, he's done a lot of work on all sorts of things like the runtime system, as you know, but also many other aspects, release management, and you should listen to what he says for this reason. All right, back to you, Ben.
All right, thanks. Thank you, David. All right, where were we here? So, all right, so as you recall, we've now have a rough idea of how execution works, right? We should now know what the STG machine sort of consists of and the modifications we've made in our C++ implementation of it. We have an idea of what heap structure and how stack usage works. So let's now look at what the runtime system does to make all of this possible, right? So this is going to begin with what is in many ways the heart of the runtime system. That is the storage manager. That is the bit that is responsible for, am I on, by the way? Okay, all right, good. The part that is responsible for allocation of the nursery, for garbage collection, and the like. So, really, storage management is actually pretty tricky business, right? We need to be able to work on a variety of platforms with a variety of different memory management primitives exposed. We don't know a priori the size of the heap that we're going to end up with, of course, so we need to be able to sort of incrementally add to the heap size of our program. We need to be able to offer allocations to the mutator in some efficient manner. Be able to allow the garbage collector to free those allocations as necessary, and we want to be able to reuse that memory, obviously. We need to be able to, because of static objects, we may have both objects that live in the dynamic heap as well as static objects, and the garbage collector needs to be able to distinguish these. We need to be able to know whether a particular object lives in the dynamic heap or not. And that's this efficient membership query. This is, whether, And we need to be able, for garbage collection purposes, it's very helpful to be able to associate some amount of metadata with groups of closures. Finally, because of modern machines being what they are, non-uniform memory access costs are very common. At this point, more common than not. NUMA here stands for non-uniform memory architecture. I probably should have expanded that. And we really want to be able to, especially on larger machines, take advantage of knowledge of the memory topology, sort of the costs associated with accessing memory from various cores, and be able to use our memory sort of wisely across those cores, using the cheap memory where we can. So in order to accomplish all of those requirements, in order to sort of fulfill this, this task, GHC bases its runtime system on a block allocator. All right? And in this case, we're going to sort of consider this to be sort of a two-level hierarchy of allocators. Right? On the outside, we have a mega block allocator. This is an allocator that is going to request relatively large blocks of memory from the operating system, typically on the order of a megabyte. And these are actually of uniform size. I should say they are a megabyte currently. And we're going to, it's responsible for somehow requesting these from the operating system in a sort of incremental manner. We again want to know, we don't know the cost, how big the heap will grow to be, so we can't allocate, the eventual size of the heap. But we also, it's very useful if the heap ends up being a contiguous block of memory, right? Because that makes that membership query that I referred to on the previous slide very efficient, right? We can just say, is the address between the beginning of the dynamic heap and the end of the dynamic heap? And that's how we can determine whether an address lives in the dynamic heap. So the mega block allocator is sort of uses virtual memory tricks to make that possible, to allocate a whole, or to rather reserve a large block of memory. Often on many platforms we'll do this, to reserve a large 1 terabyte block of memory, for instance, a block of address space rather, without actually committing any physical memory to that reservation, and then as necessary sort of claim physical memory actual memory to back that reservation. So the mega block allocator is responsible for this sort of management of mega blocks. We then split each mega block into a set of smaller blocks, right? And these are typically of much smaller size, on the order of a page or 4 kilobytes on typical platforms. And moreover, we're going to, these are both mega blocks and blocks are aligned to their respective sizes. And we can then say that we're going to say the first block is not going to contain data. Like, these are all going to contain, these are the things we're allocating. But the first block is going to contain a set of block descriptors. This is the metadata that we wanted to associate with these blocks. So every block has associated with it a block descriptor. And the nice thing about this whole layout here is that we can, in constant time, go between and addressing this block and its associated block descriptor. And in particular, not only in constant time, but just using the sort of bit operations, which is very efficient, right? And this is a very nice way to efficiently keep metadata describing our heap and its contents. A block descriptor consists of quite a bit of information. Most of this information is really there for the garbage collector. So for instance, we have a generational garbage collector, and in the block descriptor for a block, we will say which generation that block belongs to. We will say we have some way of linking together blocks into linked lists, which allows us to build sort of sets of blocks and record, this is the set of free blocks that I can allocate into, and this is the set of blocks that I've already allocated into, et cetera. We can sort of build data structures from these things. We can then as well associate information like the NUMA node, which NUMA node this block belongs to, and where we should try to use which node should be using this block as a nursery, for instance. And moreover, we have the ability to group together spans of blocks, right? If I have a block, I can say this block and the next 32 blocks that follow all belong to one block group, and therefore be able to allocate things that are larger than the block size. All right, so this is the sort of the rest of this is more or less used for the garbage collection process itself. We won't go into this at the moment. We won't actually delve that much into the garbage collection strategies that we have. We have quite a few now. That's more or less outside the scope, unfortunately, but I'm happy to discuss it after. So, as I mentioned at the outset, each STG machine, which, as we will see, this is a capability, essentially, is allocated a nursery by the garbage collector, right? And this is performed in storage.c reset nurseries, where we will, and a nursery is represented by a list of blocks, right? As we see here, a nursery consists of a block, and then it's going to have maybe perhaps several other blocks linked onto it in a chain. And the idea here is that we're going to allocate into each of these blocks in a bump pointer manner, and it's a set of blocks. You might ask, why don't we just have we said we could allocate a block group, right? So maybe we just want to, if we want a 1 megabyte nursery, allocate a block group of 1 megabyte, and then that's a nice contiguous span of nursery space that we could use. The problem with that is that would end up fragmenting the heap unnecessarily. We can very easily avoid fragmentation by using whatever sort of size of gaps in the existing megablocks that we have allocated, whatever gaps might exist. And so consequently, we allow the nursery to potentially be discontiguous. So the nursery, of course, is used for constructors and thunks and sort of normal Haskell data structures. But there's a few types of objects, compact regions, arrays, and the like, that are actually allocated via different means. They're not handled by the sort of usual HP nursery idea that we had seen previously. These are handled in the storage.c allocate function and storage.c allocate pin. These make for good reading. I'd recommend looking at them. Give you sort of a sense of how allocation works in C, which is maybe a bit more readable. How large objects are handled, etc. We won't look at this here. So mutator allocation. In the past, we saw that before performing an allocation, we first need to do a heap check, or similarly a stack check if we're going to perform stack allocation. And of course, we saw that this would take the form of something like this, right? We first add however much memory we need to the heap pointer of our STG machine. Then we check to see whether we're still within the bounds of our current heap chunk. We didn't actually look at what happened here, however. When we jumped to GC, that was sort of left a bit vague. And now we're going to clarify that. So here we have ultimately, when we fail a heap check, we're going to end up in this function stg_gc no regs, which is defined in heapstackcheck.cmm. I'd encourage you to look at this file. And it's going to sort of do a few checks to see, again, if we have more nursery blocks in our current nursery, because again, these nurseries may be discontiguous, then we can sort of avoid having to do a GC. We can avoid returning to the scheduler. We can just continue execution, set up the next heap block, nursery block rather, and then allow the machine to continue execution. However, this is only going to work if we have if we're suffering a heap overflow and if we haven't been preempted. This is actually how preemption is accomplished, is the scheduler is going to set, in order to preempt a particular capability, a particular Haskell executor, it's going to set the HP limit register to 0. We guarantee the HP limit is not mapped to a machine register for this reason. Yes?
Does that mean that Haskell threads only yield when they allocate?
That's right. Yes, that's an important point. Is you might have noticed in the past that there are some programs that you can write that seem not to be very interruptible, and that is precisely for this reason. We rely on heap and stack checks to accomplish preemption. You can actually force every function in your program to have a heap or stack check with the no omit yields flag. And so that's sort of, if you find that that's problematic, you can tell the compiler not to omit yields in non-allocating functions, and that's a way of ensuring preemption. But yes, that's a good observation. Right, and so there's a variety of other checks here. Oops, there we are. A variety of other checks. But ultimately, when if we find that we need to do a GC, or we've run out of heap or stack or the like, then we're ultimately going to pass control back to the thread scheduler. And the scheduler will likely end up calling into the garbage collector, which is of course defined in gc.c. Well, we'll see what happens in the scheduler in just a moment when we look at how GHC implements its green threading model and sort of concurrency story within it. So GHC, of course, provides threads with an M-to-N green threading model. We support bound threads, which can only run on a particular operating system thread. And so to clarify here, actually, I should say this M-to-N threading model, this means that we may have M operating system threads, and on those M operating system threads, we may have N Haskell threads, and those numbers are not related in any way, right? So moreover, those N Haskell threads are typically much cheaper than the operating system threads on which they might run. So typically, you're going to have far fewer. M is going to be much smaller than N in many cases, or can be much smaller than N. That makes for a very nice concurrency story, as you know. Now, in order to accomplish, to sort of implement this threading model, we have two principal abstractions within the runtime system. We have tasks, which represent an operating system thread that might be used for Haskell execution, and we have capabilities. And these are the concrete state of the actual Haskell executor, right? The machine state that we saw at the outset here is going to be kept in the capability context, all right? And the idea here is that we have a fixed number of capabilities in our program. This is what you're setting when you set -N or set num capabilities, essentially setting the concurrency level of the program, how many Haskell threads we can run concurrently. And this is, is bounding concurrency. Moreover, we allow the, yes, that's right. So what is a capability? Well, it consists, as I said, of a set of STG machine state. We have various, the NUMA node where we like to run this capability, and if we are, if the capability is currently actually running Haskell or if it's suspended. Moreover, capabilities are owned by tasks, so that is to say that a capability is owned by a particular operating system thread. And this allows that essentially tasks exclusive control to much of the state, access rather, to much of the state that we're going to see in the next few slides in the capability structure. Capabilities in the runtime system are released and acquired with the release capability and wait for capability functions, right? So these are functions you'll see again and again. Moreover, you may yield a capability if you already own one, sort of allowing another task to pick up that capability and execute with it with the yield capability function. Again, this is very useful in garbage collection, for instance, when we want to yield to the garbage collector. In addition, the capability is going to have a set of threads that it can run, right? It has a run queue, a set of threads that are waiting for CPU time. As we will see, there is a work pushing strategy that we use to ensure that all capabilities within the program have work when the work is available. We have various bits of GC state. So for instance, our generational garbage collector requires what's so-called mutable list, which tracks intergenerational references. And these are sort of highly mutated data structures, which we want very much to avoid contention of. And so consequently, they live on the capability, which is at any given moment owned by a particular CPU, right? And that's going to, again, avoid the contention for adding, when adding values, pointers to these mutable lists, these remembered sets. Similarly, there's a similar remembered set for the non-moving collector as well. We have sort of the allocator state, so the set of current segments for the non-moving collector, and the set of a set of allocation areas for pinned objects, again on a per capability basis, so that we can avoid contention. And we have a context switch flag, which is used by the scheduler to tell a capability that please stop executing now. I want you to return to the scheduler because, for instance, we're going to do a garbage collection. So these are again, in the capability state. Of course, at times there are events that require that one capability notify another capability of something happening, right? And so two examples of this might be if you have one thread running on capability A, which has currently evaluating some thunk, and you have another thread on capability B which wants to enter that thunk, and that thunk has been black holed, as we saw previously, then the capability B thread will send a message to the evaluating thread saying, I want to block on that thunk that you're currently evaluating. And it's the capability A's, at which point capability A is sort of on the hook to notify capability B when that evaluation has finished and wake that thread up again. Moreover, asynchronous exceptions are another example of this. I want to interrupt the thread that you're currently executing. We have as well, message delivery is mediated by another field, the inbox field of the capability structure. And finally, this brings us to Haskell threads, right? So capabilities are sort of the substrate on which Haskell evaluation occurs, but then the threads themselves are this separate data structure, which are actually, these are heap objects. These are TSOs, or thread state objects. And we see here we have this header field, which is a sure sign that we are dealing with a heap object or perhaps a stack frame. And we see that TSOs have quite a bit of state themselves. So in addition to having a pointer to their stack, they have if they are blocked, what they are blocked on, whether they're executable or not, if they are bound to a particular task, which task, the capability that currently owns that thread. So for instance, if that thread is on a run queue, which capability's run queue is that? You can label threads, etc. A list of threads that are blocked on thunks that are under evaluation by that thread. These are all things that are relevant here in TSO. Additionally, we have the ability to form lists of TSOs as well. Linked lists are a very common data structure in the runtime system, and they're often how we form sets of things. As I mentioned earlier, scheduler does have some mechanism for work pushing, right? So if a capability finds that it has a surplus of threads, more than one, for instance, in its run queue, then it will, in the scheduler, look for other capabilities that have a sort of dearth, a lack of threads, and will claim those capabilities because they must be idle, right? So we can the scheduler of one capability can claim another capability as well, mutate its run queue to add the new excess thread to that run queue, and then wake it up to allow it to initiate evaluation of that thread. So that is sort of a very, very brief overview of the scheduler and sort of the basic primitives involved in concurrency. Are there any questions so far? That was very quick, I'm aware, but I'm happy to take time here to. Okay, it's either a good sign or not a great sign. Oh yeah, hello.
So a capability can have multiple threads running on it.
That's right. One at a time, of course, but yes.
One at a time. They would need different stacks?
That's right, yeah, because the stack is a property of the TSO.
A stack is a property of TSO, okay.
Yeah.
I think I was confused because you said a capability is like an STG machine, and previously we associated the stack with the STG machine, but actually the stack belongs to the TSO running on the machine, as it were.
So when we initiate execution of a stack on a particular capability, we will set up we'll take the stack from the TSO, and we will place that in, the SP and SP limit in the appropriate machine, STG machine registers. Now, one thing to note, though, is that the nursery is a property of the capability, right? So that is to say that all of the allocations of any stack, of any thread rather, a Haskell thread running on a particular capability will all end up in the same nursery. We don't distinguish, we don't separate allocations from different threads.
Right, and then if the capability switches to executing a different TSO, it will need to swap the stack pointers.
That's right.
Yeah.
Yeah.
Okay.
Precisely. Okay. Yeah. Oh, we have a few. Okay. Quite a few. Oh no. Okay. That's good though. That's good. I take it back.
Can you specify the number of tasks that you want for your
No.
Haskell application?
No. You cannot.
Is that number something like capabilities plus something? Like number of capabilities
It's
plus something?
dynamic. So if you say foreign calls in particular may cause additional operating system threads to be spawned to run that call, and that will result in an additional task as well.
So earlier you said that the queue for threads that were waiting on the data to be evaluated was on the capability, but now you're showing it.
Yes, it's a good
TSO,
point.
So.
So the thread is owned by a particular capability, and thread B, owned by capability B, wants to block on a Thunk owned by thread A, right? The black hole will point of that Thunk will that Thunk will be a black hole at that point, and the indirect T, as we saw previously, will point to TSO A, right? The thread A, and so you'll note here that we have an owner, the capability field here, which allows us to know which capability owns that thread that is doing that evaluation. And we will send a message from capability B to capability A, which will then add it to, look up that thread and add it to the appropriate threads blocking queue list.
What if that thread isn't active right now?
Oh, that's okay. That doesn't need to be running. It will be on the run queue at that point. So we'll look at the run queue and we'll see.
Right, but it doesn't have a capability.
Well, it doesn't. It's not running on a capability, but it's still owned by that capability. If the thread is, it may not be running, but if it's on the run queue of a capability, it is owned by that capability.
I see.
Yeah. I think we had one more. Was that it, Lyle?
Well, I am curious about how the message queue works, but maybe you'll.
Okay, let's. Yeah, maybe. Happy to answer after. We're running. I think we're probably down to 5 minutes now, so it's thankfully 7 minutes. Okay.
You said that one thread could mutate another thread's queue, or wait, what was the specific term?
So the blocking queue, no, that's actually why we have this message passing scheme, is to avoid having to mutate the state of one capability or one thread from another, one TSO from another capability. So yeah, we ensure safe. Sort of safe concurrent mutation via this message passing scheme. That's the strategy.
Okay, thanks.
Yeah. Great. Okay, we don't have that much more to go through. I was going to go fairly quickly through the bits that remain, actually. So we are now going to look a bit at the moving parts of GHCI. This is an important piece of the runtime. Not most interested, the most glamorous. Linking is kind of a rather tiresome subject, but we're going to go very quickly through the RTS linker. In particular, GHC's runtime system includes a static linker and loader for the platforms that it supports, Windows, BSDs, Linux, and Darwin. And the idea here is we want to be able to load object files and static archives that come directly from the compiler. They're not executables or shared objects. They haven't been sort of gone through a final link yet, as you would in an executable context. But we nevertheless want to be able to load them. And why? Well, you might think we have dynamic loading in most platforms, right? The dynamic linker is a great option when it's supported, often. But there are some reasons why, actually, in the case of Haskell and GHC in particular, often it's not quite sufficient. So portability is a problem. Not all platforms support have a very featureful dynamic loader. There are performance penalties that you may need to pay, and moreover, garbage collection, particularly required for code unloading, is very tricky with dynamic loading because of the lack of insight into the object structure that the dynamic loader provides. So we have this static loader. Linking, the principal abstraction of this piece of software is the object code abstraction. This represents an object file, essentially. I will refer you to linker.c and RTS for details here. Essentially, there's a few different phases of loading. And after an object has been loaded, it can be unloaded, which requires cooperation from the garbage collector. Since there may be references to static objects living in that object, static objects living in that object file, which we cannot, which we have to keep alive until, which we have to keep alive. Mapping is quite tricky. We have an allocator specifically for this task to ensure that we don't violate jump displacement restrictions of the platform that we are linking for. This is called the M32 allocator. I'd again refer you to the relevant implementation. I'm happy to discuss it after. We also have a bytecode interpreter. This is used for interactive evaluations. So in particular, compiling object code is quite expensive. So for interactive usage, like in GHCI and template Haskell, we generally try to prefer a bytecode, which is much quicker to load and not execute. It's not a very high, the runtime cost is fairly high. But the loading and compilation cost is much lower. So it's often a good trade-off. This is a stack machine. Has a very simple 16-bit instruction set, which can be found described here. And the interpreter itself that interprets that machine's instruction set is defined in in the runtime system. So working on the runtime system, this is, I'm going to skip this slide actually. There is code in the runtime system. There are header files as well. You should try to use rts.h. There are both private and public symbols. And the public interfaces are defined in rts.h. The private symbols are hidden from end users to avoid namespace noise. There's a variety of ways of validating runtime system behavior. So we have assertions, which are only compiled in the debug runtime, and checks, which are always asserted. These are macros, CPP macros, and very useful. You should use them when possible. Valgrind can be sometimes useful for diagnosing C-side leaks, but generally is not terribly useful for Haskell issues, in the mutator, because Valgrind has no insight into the Haskell heap structure. Thread sanitizer can be very useful for catching data races and concurrency. The GHC's runtime system is a rather complex concurrent system, and we have quite a bit of lock-free logic in there, and therefore is ripe for data races. So thread sanitizer is a very useful tool in that regard, and I'd refer you to that note. There are a variety of observability tools that you can rely on. Debug belch being the simplest, it's just printf to standard error in most cases. But the event log can often be much more useful when you have large quantities of data. It's easier to filter, and there are a variety of means of getting data into it. It's also enabled by default now in the runtime. You don't need to enable it explicitly. And we have these various debug flags, plus RTS-D, G, S, capital S, etc., which enable various tracing or output and checks. In particular, plus RTS-capital D, capital S enables the sanity checker, which will essentially assert the sanity of the heap state and stack state of the program at every GC and at various points during evaluation. Very useful for catching soundness issues and the like. strace can be obviously useful. And GDB, I'd point out, is very useful in conjunction with RR, which is a time-traveling debugger, which you, if you work on this sort of thing, should absolutely know about. And you should use the plus debug info flavor transformer whenever working on this sort of thing. It makes the debugger output significantly more useful. There are various, we have a symbol name convention. It can be very useful to know this to be able to understand the symbols that you see on the stack and in the heap. I will leave that for your own reading. I give a list of recommended readings in the slides. Do have a look. There are some great papers in there and in the references. And I think that brings us to the end. So if you have any further questions, I think we're out of time.
That's right. Please take further questions in the breaks and all around.
Yeah, happy to answer anything that you might be interested in. And thank you for listening.
Thank you so much.
Yes.